the last video, I explained how the adjacent hydrogens will split into this particular NMR signal, and that the intensities of the peaks and the number of peaks will, so there'll be n plus 1 peaks for n adjacent hydrogens, and it will take the ratio 1 to 2 to 1 for a triplet, and 1 to 3 to 3 to 1 for a quartet, etc., because there's some overlap. In this video, I want to address what happens when the hydrogens that are adjacent to a given hydrogen are not magnetically equivalent to each other. And a good example of that would be an alkene. And I'm going to put a T-butyl group here. So that this system itself is isolated and has no adjacent hydrogens. The three CH3 groups that are attached here will have a chemical shift of about 0.9 parts per million. That'll be a large singlet with an integration of 9 hydrogens, and we'll have no coupling constants because there are no adjacent hydrogens on any of those. Sometimes with a really intense peak like this, you do see what we call 13C satellites. C is only about 1% natural abundance. But it is an NMR active nucleus that has a spin of 1/2 and thus an alpha and a beta state. So if this hydrogen happens to be a 13C, or this carbon rather happens to be a 13C, the 3 hydrogens that are attached to it will be split. And the coupling constants are large. But because the likelihood of a 13C being there, the peaks are rather small. So what we should expect to see at 0.9 parts per million is a really big singlet. And then on the outside, the 13C satellites. These are the 13C satellites. We usually don't see them for most peaks, but in this case, since it's 9 identical hydrogens resulting in a really large singlet, sometimes we do see those 13C satellites, and we just ignore them, they're not important. This other system here is a distinctive pattern which is referred to as an ABX pattern. The chemical shift of these two hydrogens, A and B, would be similar. Because they're attached to the same carbon. But they're not magnetically equivalent because one of them is on the same side of the ring or the double bond as the T-butyl group, and the other one is on the same side as the other hydrogen. This hydrogen will be different in chemical shift significantly because of the presence of the adjacent T-butyl group. And it will be shifted further downfield. Because the presence of the T-butyl group is electron donating, there's hyperconjugation going on here where there are electrons being donated in. That makes the electron density larger at the end of the pi system that's substituted with the T-butyl group. And if the electron density is larger at this end, the induced magnetic field will be larger. Recall that for the pi system, the induced magnetic field, or the local magnetic field caused by electron circulation, reinforces the applied field. So you'll have a larger HI here than you will here. I'm likely exaggerating the difference, but the larger HI here will cause the effective magnetic field to be larger at HX. And as we know, if the effective magnetic field is larger, the alpha beta gap energy is larger and we go to a higher frequency. So I'm going to propose that we say that this shows up at about 6 parts per million, and these two probably show up somewhere between 5 to 5.5 parts per million. I'm not sure if that's actually true for this specific system, but those numbers would be reasonable estimates. So we should see 3 separate signals for this ABX pattern, and they will all be split. So let's look at HX first. and propose that we put the 1800 hertz additional energy in to shift it so that Hx is all in the beta state. And then Hx is going to talk to HA and HB and effectively ask them what they're doing. What's the situation at hydrogen A and hydrogen B? And hydrogen A might say alpha, and hydrogen A might say beta. And then hydrogen B might say alpha as well, or hydrogen B might say beta. So as usual, we have 4 different answers. Roman numeral 1, 2, 3, and 4. For n adjacent hydrogens, 2 adjacent hydrogens in this case, we have 2 to the n possible situations. Both alpha, hydrogen A alpha, hydrogen B beta, hydrogen A beta, hydrogen B alpha, and hydrogen A and hydrogen B both beta. When hydrogen A and hydrogen B were magnetically equivalent because they were a CH2 group, these 2 situations gave rise to an identical overall effective magnetic field. But if HA and HB are not magnetically equivalent, they are not creating the same magnitude of induced magnetic field. And in fact, the coupling constant is quite different for a trans coupling constant, JAX, which is a trans coupling constant, this one. The coupling constant tends to be somewhere between 12 to 16 hertz, significantly larger than an overall alkyl coupling. JBX, the coupling constant for the cis hydrogen, is smaller. It tends to be between 6 to 10 hertz. And the 2 hydrogens that are on the same carbon, because they're magnetically different, will couple to each other. But that's a geminal coupling on an sp2 hybridized carbon, and a geminal coupling constant on an sp2 hybridized carbon is small, somewhere in the 1 to 3 hertz ratio. So we have distinctly different coupling constants, and those distinctly different coupling constants result from distinctly different magnitudes of the induced magnetic field generated by the adjacent hydrogen. So the trans hydrogen here, HA, is going to generate an induced field that's either reinforcing or opposing the applied field. And HB, the cis hydrogen, is going to generate an induced field, but it's going to generate an induced field that is smaller than the induced field generated by HA. So if we look at the overall picture, and we have the same applied field in all 4 cases, and then we add the magnetic field vectors generated by hydrogen A and hydrogen B, we'll have one situation where it's shifted significantly further downfield because the effective magnetic field is now significantly larger. Number 2 will have that reinforcing HI from hydrogen A, but then we'll have an opposing HI from hydrogen B But notice that it's not canceling out all of HA because it's a smaller magnitude. So our effective magnetic field does not go back to the original as it did when the two hydrogens cancel each other out. For Roman numeral 3, we'll have HI from A opposing, and then HI from B reinforcing, but not going all the way back. So we'll have an effective magnetic field. It's actually a little bit less than the applied field. It's a little bit shielded relative to the applied field because HA is shielding it a bit, and HB is de-shielding it, but not by as much. And then for Roman numeral 4, both A and B are opposing, shielding it a little bit, and we'll have another H effective. If we go across, I think you can see that all four of those H effectives are different. Which means that we will actually see 4 different peaks. So it doesn't follow the n+1 rule. It follows the 2 to the n rule. There are also non-first order splitting patterns that fall somewhere in between n+1 and 2 to the n. The minimum number of peaks for n adjacent hydrogens that you'll see is n+1 in the case where they're all magnetically equivalent. The maximum number you'll see is 2 to the n in the case where they're all magnetically different. But if some are magnetically equivalent and some are magnetically different, then you will see somewhere in between those 2 peaks. So in this case, we see 3 peaks for 2 identical and 4 peaks for 2 non-identical. And that's really the only possibility for 2 adjacent hydrogens. We can draw a splitting tree that matches this by starting at 1800 hertz with an intensity of 2 to the n. So the intensity of 4. And then applying the coupling constant JAX and the coupling constant EX. It's generally the best practice to avoid overlapping peaks if you use the largest coupling constant first. So I'm going to take the middle of the range here. And I'm going to say, let's call this 14 hertz. And I'm going to take the middle of the range here and say, let's call that 8 hertz. But you could do the coupling constant tree for any number. So under the influence of hydrogen A, we're going to split this peak. So you see 2 peaks 14 hertz apart. So we're subtracting 7 hertz or adding 7 hertz. And we'll see 2 peaks at 1807 hertz and at 1793 hertz. So this is JAX, the larger coupling for the trans hydrogen. And then we'll apply JBX, which will split each of those into 2 peaks that are 8 hertz apart. So minus 4 hertz and plus 4 hertz in each situation. So instead of seeing a peak at 1793, we'll see a peak at 1789, and we'll see a peak at 1797. And instead of seeing a peak at 1807, we'll see a peak at 1803, and we'll see a peak at 1811. The intensity will have been switched to 2 when we split that into 2. And then when we split each of them again, the intensity will be equal to 1. So the 4 peaks here will be of equal intensity. And this is what we call a doublet of doublets. RDD for short. Right? You'll notice that the two middle peaks don't go back to the original 1800 hertz now. They are now 6 hertz apart. And that's why we don't see a 1 to 2 to 1 triplet, because these two peaks do not come back on top of each other. We would report this as delta equals 6.0 ppm integration, and then J is equal to, it doesn't matter what order, we list the coupling constants. If we started with 8 hertz and then split each of those by 14 hertz, we would get an identical pattern. We would just have an inconvenient overlap in the middle. And you can test that theory at home. You can do the 8 hertz one and the 14 hertz ones in the opposite order and confirm that you still predict 1811, 1803, 1797, and 1789. So this is a doublet of doublets. We could do exactly the same analysis for hydrogen A, which would have a splitting from HX of approximately 14 hertz, and then a splitting from HB of maybe 2 hertz. And we could do the same for HB, which would have a cis coupling of about 8 hertz, and then a geminal coupling of about 2 hertz. It is always true that if one hydrogen splits an adjacent hydrogen with a coupling constant of 8 hertz, the adjacent hydrogen will in turn be split by it with an identical coupling. One of the things that helps you identify hydrogens that are attached to each other is when you see identical coupling constants. So we would expect for that region from 6 to 5 ppm to see a downfield doublet of doublets for hydrogen X, and then slightly further upfield, we would expect to see 2 additional doublets of doublets. But now the second coupling constant will be very small. Something like that. Something like that. You'll notice that this pair of doublets, which is a little bit messy, this pair of doublets are closer to, or further apart than this pair of doublets because JAX is a little bit bigger than JBX. We can go from the pattern back to a splitting tree by connecting the adjacent hydrogens, or the adjacent peaks rather, and then connecting the center of those. This would be JAB, this would be JBX, this would be JAB, this would be JAX, and here we're looking at JBX, JAX. Because A and B are quite close to each other, it's not unusual for these peaks to overlap with a relatively low field instrument, low magnetic field. One of the reasons for going to a more expensive, larger electromagnet, a higher resolution instrument like a 400 megahertz instrument instead of a 300 megahertz instrument, is because the coupling constants are not field dependent. It's always going to be the same 8 hertz coupling constant for JBX regardless of the field, but the number of hertz between 5 and 6 parts per million will increase from 300 to 500. Closely spaced peaks will overlap at low field and not overlap at high field. This pattern is one of the patterns that you'll learn to recognize, this AEX pattern, where you have 2 similar chemical shifts and then one that's quite different, and the coupling constants match. I didn't do a very good job of drawing this to scale. But if I had drawn it to scale, this AX distance should be the same as that, and this EX distance should be the same as that, since they're coupled to each other with equal magnitude coupling constant. So you notice that the 2 hydrogens there, A and B, that are attached to the same carbon, are non-magnetically equivalent and split each other. It's also possible for two hydrogens attached to an sp3 hybridized carbon to be non-magnetically equivalent and thus split each other. And you'll see that often in cyclohexane rings. If I conformationally lock this ring by putting a T-butyl group there so that we cannot have any chair-chair conformational flipping, this hydrogen is axial, and this hydrogen is equatorial. And if they stay axial and equatorial, they're not in the same magnetic environment, which means they'll split each other. The coupling constant for geminal on an sp3 hybridized carbon is usually quite large, 14 to 18 hertz, generally even bigger than the coupling constant for a trans-vicinal relationship. So if we look at this equatorial hydrogen, the equatorial hydrogen is split by HA here, H axial, with a large coupling constant, but it's also adjacent to two axial hydrogens on other carbons and one equatorial hydrogen on another carbon. These two are magnetically equivalent. But the other two are not. So if we actually looked at this signal for the equatorial hydrogen, we would expect it to be split into a doublet from HA, into another doublet from this equatorial hydrogen here, which I'm going to call HB, and then a triplet from the combined interaction of the two axial hydrogens. The coupling constant for adjacent hydrogens like this is dependent in a mathematically known manner on the dihedral angle. And since the dihedral angle is 180 degrees for both HC and HB, with respect to H axial, it should be the same, and the dihedral angle from H equatorial to HC and HB in both cases is 60 degrees, and so the coupling constant should be the same for HCE and HEE. So we should have JAE somewhere in the middle of that range, maybe 60 hertz. And then we should have JBE. And because that's a 60-degree dihedral angle, 60-degree dihedral angle is usually 3 to 4 hertz. And then we have JCE equal JEE. And again, since that's a 60-degree dihedral angle, that's typically 3 to 4 hertz. So even though hydrogen B is not magnetically equivalent to hydrogen C and D, and in fact hydrogen C and D aren't really quite magnetically equivalent to each other, because HC is on a carbon that has the hydroxyl group, and HD is not on a carbon that has the hydroxyl group, their coupling constants are going to be approximately the same. Magnetically equivalent, same alpha beta gap. But you might have the same coupling constant even though you are not magnetically equivalent. I should actually change that. These are not magnetically equivalent, because one's going to be much further downfield. HC being adjacent to the hydroxyl group is going to be somewhere around 3.5 ppm, whereas HD is not going to be at 3.5 ppm. So these are all magnetically different hydrogens. This one probably will be closer to 1.5. There will be some coincidental overlap. So if we assume that these three coupling constants are all about the same, at 4 hertz, and we went to draw a splitting tree, we would start with a very large coupling constant, 16 hertz apart, minus 8 plus 8, and then we would go to a much smaller coupling constant, where there's only a 4 hertz difference, minus 4 plus 4. then do another 4 Hertz coupling constant. Minus 4 plus 4. So those two peaks would now overlap. And then we would do a third identical coupling constant. Again, minus 4 plus 4. And we do the same on this side. And I haven't drawn this to scale. Because you'll notice if you lose 8 here, but then you gain 4, and then 4 more, so these are 2. Mess it up. 4 Hertz difference, which means it's minus 2 and plus 2. So JAE has split our original peak. And let's just arbitrarily say that it's at 300 Hertz. So peaks at 292 and 308. But then under the influence of JBE, JCE, and JDE, we have a peak of 294 and 290. And then we have a peak of 296, back to 292, and 288. And then we go another 2, and we've got a peak at 298. This peak is back at 294. This peak is back at 290. This peak has lost 6 and is back at 286. So it hasn't quite made it all the way back. Here the 308 peak is shifted into peaks at 306 and 310, and then 312, and then 314. And then 4 Hertz different, this peak will be at 310. This peak will be at 306. This peak will be at 302. So as I said, I haven't quite drawn it to scale because the distance between these two peaks, when you do it, which should be identical to the difference that you see between any adjacent peaks. Each of the original doublets is split into a 1 to 3 to 3 to 1 quartet. So what we should expect to see as a pattern for those 4 adjacent hydrogens is not 16 peaks, which is what we would see if it was 2 to the n, but it's also not 5 peaks, which is what we would expect to see if it was n plus 1. What we really see is a doublet of quartets. We would abbreviate with a DQ. And we would report this as delta equals 1 part per million. dQ representing 1 hydrogen. J is equal to 16 Hertz, 4 Hertz. It's important that in this case that the one we list first is the one that's corresponding to the doublet. And the one we list second is the one that's corresponding to the quartet, so that we know which is the coupling constant that's applied only once and which is the coupling constant that's applied 3 times. Right? This is referred to as a non-first order splitting pattern. It doesn't follow either the 2 to the n rule or the n plus 1 rule, but it's in between. The maximum number of peaks we could possibly have for 4 adjacent hydrogens is 2 to the 4th. there are 16 possible ways for these 4 adjacent hydrogens to be either alpha or beta, 16 different combinations. But you'll notice that not all 16 of those are unique in this case, because we've got this overlap as a result of 3 identical coupling constants. The only way to get good at this will be to practice it, and using graph paper or ruled paper turned sideways, you'll be able to do it to scale